Good morning all and welcome to the online class of NPTI Durgapur. Today the subject of discussion will be generator synchronization and capability curve of the generator. To guide you through the presentation, we'll be revising the basics of generator, the principle of generator, what are the basic construction of generator. These all things we'll be discussing here. Then we'll be going to the startup sequence of generator. Gradually, what steps are taken to start a generator. Then we'll discussing the pre-synchronizing checks, means before synchronizing what are the important parameters that needs to be checked and verified whether they are healthy or not. Then we'll be going to the synchronizing conditions. And last we'll be discussing about the generator capability curve. What is this curve and why is it used for? We'll be discussing in this and we'll be plotting this curve. Now coming to generator basics. What is a generator? We all must be knowing that generator is an electrical device that converts mechanical energy into electrical energy. And the principle that governs this conversion is the Faraday law of electromagnetic induction. So, what is Faraday law of electromagnetic induction? Faraday law states that whenever a conductor is cut by a flux, then an EMF is induced in the conductor. This means that whenever a conductor cuts a flux or a flux cuts a conductor, laying it in more simple way, whenever there is a relative motion between the flux and the conductor, an EMF will be induced in the conductor, and this EMF induced will depend on the rate of change of flux that is linked to that conductor. So EMF induced mathematically, if we write it, will be proportional to d phi by dt, and if there are n number of turns, then EMF induced will be proportional to n d phi by dt. So this is what Faraday law of electromagnetic induction states, and a generator runs on this principle. Now, second law that comes into play is the Lenz law, because Lenz law decides the direction of the induced EMF. So what does it state? Lenz law states that the EMF will be induced in such a direction so as to oppose the cause that produces it. Now here, what is the cause that is producing the EMF? It is the rate of change of flux, that is d phi by dt is causing the EMF. So the Lenz law says EMF will oppose the cause, means it will oppose d phi by dt. So what we get? We get EMF is proportional to minus n d phi by dt. This minus comes because of Lenz law. So this both law combined together gives us E is proportional to minus n d phi by dt. So when the circuit will be closed, a current will flow. Now in a thermal power plant or in a plant which is synchronized to a grid, we basically use a synchronous generator. So what is a synchronous generator? Synchronous generator is a generator that runs at synchronous speed. Now what's synchronous speed? We generally represent synchronous speed as ns is equal to 120 f by p, where f is the frequency and p is the number of poles of the generator. So in India we have a frequency of 50 Hz. So here f will be 50, and suppose we have a thermal power plant in which the generator has 2 poles. So here ns will be equal to 120 into 50 divided by 2. So this comes to about 3000 rpm. So in an alternator that is running at 3000 rpm, this is running at synchronous speed. Suppose we have another generator, suppose it is hydropower plant generator that has 4 poles. So synchronous speed for this generator will be 120 into 50 divided by 4, that comes to about 1500 rpm. So if you classify a generator on the basis of this speed, we will have two classifications. One will be a synchronous generator that is running at synchronous speed. Second will be asynchronous generator that is not running at synchronous speed. Again, this asynchronous generator can be classified in two broad heads again. One will be that is running above synchronous speed, that is super synchronous, and second one will be that is running below synchronous, that is the subsynchronous, and the subsynchronous basically we know it by the name of induction machines. Will not be going into that detail. So we are discussing here is a generator runs and in the principle of Faraday law of electromagnetic induction, and for an alternator or synchronous generator the RPM that it will run will be equal to synchronous speed. Now coming to the construction of a alternator or a synchronous generator, it is broadly classified that it has four parts. One is the stator, second is the rotor, third is the excitation system, and fourth one is the cooling system. So coming to stator, as the very name suggests, it is the stationary part of the machine and is made up of special magnetic material which can allow high magnetic permeability and low magnetic hysteresis such as fabricated steel. Stator core is laminated to minimize the effect of eddy current losses. The lamination is insulated from each other by a thin coating of an oxide and has a space between them to allow passage of cool airflow. The slots are provided in the inner periphery of the core and the armature conductors or coils are assembled in it. The armature winding of the alternator is usually connected in star and the neutral is connected to the earth through a neutral grounding transformer. Second one is the rotor. The revolving structure of the electrical machine is called the rotor. In a synchronous generator, rotor generally carries the field winding which is supplied by a DC source. This DC source is called the excitation system. Rotors by virtue of its construction are of two types, salient pole type and non-salient pole type, or the second one name is cylindrical type. Salient pole type, this type of rotor, the air gap between the rotor and the stator is not uniform. The poles of the rotor are projecting in outward direction. Salient pole rotor can be used for low speed applications which are generally below 1000 rpm. Cylindrical pole type rotor, this is used for turbo alternator which run at a very high speed. In this, the air gap between the rotor and stator is uniform throughout. The third part is the excitation system. We provide DC power in the excitation system. Generally in a high machine or a bigger capacity machine, the excitation system is fed in the rotor which is called the field winding. Excitation system can be AC or DC. Generally in a large machine we have a AC excitation system which is generally of static excitation or brushless excitation. This has already been dealt in detail in the excitation and AVR system class. Now, why is the armature winding in stator? This is a general question. To answer this, at a high voltage, it is easier to insulate the stationary winding, which may be as high as 25 kV or even more in some cases. The generated high voltage output can be directly taken out from the stationary part, whereas for a rotating armature there will be large brush contact voltage drop. Also, the sparking at the brush surface will be a problem to look after. If the field winding is on the rotor, low DC voltage can be transferred safely to the exciter winding via slip rings. The armature winding can be braced well to prevent deformation because at a high centrifugal force if it was in the rotor. This means if the field winding is in the rotor, the weight of the rotor is not so much, so the centrifugal force can be balanced. But if the armature winding was in the rotor, Due to its weight, it would be difficult to balance the high centrifugal force. Now coming to the fourth part, that is the cooling system. Whenever current will be flowing in a circuit, it will produce a heating effect. So in a generator, we have stator winding and rotor winding, and both are carrying current. So both will be heating up. We need a system which can cool the heating effect of the current carrying conductors. For that, we have cooling system. Lower capacity generator may simply be air cooled. As we move in higher rating capacities, the air cooling changes to, it may be hydrogen cooled, rotor can be hydrogen cooled, and stator will be water cooled. This slide shows the four parts which we have discussed, that is the stator, rotor, excitation system, and the cooling system of the generator. Now let's discuss the startup sequence of a generator. First, the turbine RPM is increased from 0. The generator rotor is directly coupled to the turbine. So as the RPM of turbine increases, generator's rotor RPM also increases. Next step is closing of field breaker. This breaker cannot be closed at low RPM, because if we close it, the generator will trip in overflux protection. So we need to increase the speed of the generator. Once we reach a speed of 2800 and above, the field breaker is closed and simultaneously a field flashing command is given. Now, what is field flashing? When a generator is rotated by external force, then the rotor bars cut the magnetic fluxes generated by residual magnetism property. By cutting those fluxes, a small amount of EMF is induced in the armature. This is basically the Faraday law of electromagnetic induction, which we have already discussed. Now, residual magnetism in the generator excited field allows the generator to build up voltage during startup. This magnetism, that is the residual magnetism, is sometimes lost due to shelf time or improper operation, among other reasons. Restoring this residual magnetism is possible, and this is sometimes referred to as flashing of the exciter field. So now once this is done, we put the voltage in auto command and give a reference set point. Suppose we have a 500 megawatt generator and the terminal voltage of the generator is 25 kV. So we give a set point of 25 kV. Now once 80% of the terminal voltage is reached, this is 80% of 25 kV is reached, the field flashing will automatically stop and thyristor firing or the exciter firing will start. Means main exciter will come into the picture. Gradually the RPM of the generator is increased and it reaches the full speed, that is the 3000 RPM, and the voltage also reaches the rated voltage. If any adjustment is required, then we can change the auto reference set point accordingly. Then the generator is synchronized to the grid and it starts delivering power to the system. Synchronizing in details will be discussed in our next slide. Now this slide shows the logic of field flashing. So for field flashing to be on, what are the logic? First was the generator RPM should be greater than 2800 and excitation command should be given, that should be on, and all the faults in the generator protection relay should be reset. If these three condition is there, then field flashing will be on and field breaker command will also be on. Now once the terminal voltage reaches 80% and when the field breaker is on, then the output will be, the field flashing will be off and the converter firing will be takes its place, that is main firing system will come into the picture. Now, before we start the synchronization process, all the auxiliary systems should be in good operating conditions. So we need to check these auxiliaries. These auxiliaries include the hydrogen system. The hydrogen is used for cooling the generator rotor. Then the seal oil system that is used to seal the hydrogen so that there is no impurity ingress in the hydrogen. Then stator cooling water supply system. Then a cooler cooling water supply system. Then is the bearing lubricating oil system and the jacking oil system. Apart from these, others are also important to be checked, but these are critical since when the system comes into service, these will play a vital role. Now there are few synchronizing checklist in generator even. Now, as we have discussed that the generator stator winding is star connected and is grounded through NGT, and there is a neutral grounding resistance cubicle. So we must check that cubicle properly and they must be properly sealed. Then all the CTs that are connected in a generator, that can be the phase CTs, that can be the neutral CTs, that can be the group protection relay CTs, because the CTs must be properly connected and sealed. Proper connection I am telling is because there is a protection that CT cannot be open-ended because it might create an explosion. So yes, so in order to prevent that, we must particularly check all the CTs, namely the phase side CTs, means R by V phase has the CTs, then the neutral CTs, then the current transformer that are giving the input to the generator protection relays. All these should be properly checked and their cubicle must be sealed so that no external person can interfere with that. Then generator links, flexi links, generator has flexi links that is going to the generating transformer. We must check that is properly tight in the phase and the neutral side. Then generator protection setting needs to be cross-checked and verified so that if any abnormal condition comes after or while synchronizing, generator may be protected. Then the DC supplies to the relays should be properly checked. Generator winding and bearing temperature should be normal and they must be appearing in all the places in the local as well as in the DCS. Now there will be a few pre-synchronizing checklists of the excitation system even. We must check all the carbon brushes are properly installed or not. All the carbon brushes must be properly pressurized to the ring so that there is no sparking when the generator comes into operation. The excitation transformer is there. So the temperature of the transformer should be normal and the cooling system of the transformer should be healthy. Then we must see that cleaning air filters are healthy. Inspection of AC duct, flexi link, as we have checked in the generator case. In this also we need to check they are healthy or not. Then CT and VT connections of the AVR should be checked and properly sealed. Then inspection of the DC bus duct, flexi links on generator and excitation system, IR value, tightness, etc. of the AVR and excitation system should be properly checked and their value should be proper. And after this is done, and after we find that the generator, AVR system and the mechanical side of the system are healthy, then we go for synchronizing the generator to the grid. And so we start with the process of synchronization that will be dealt in the next slide. What is synchronization? When we have two independent sources of power generation, then we need to synchronize them to make them operate in parallel. Now first we come to an example to understand this. Suppose we have a generator as a backup in our home. Whenever the power goes, we start the generator. You'll notice that the generator and mains are not connected directly through one input. What I mean is that you'll notice that the generator and the mains are connected with a three-way switch. One side of which has the main supply, other side has the generator supply, and the middle one is in the off position. This off position may or may not exist in some cases. This means that the generator and our main supply cannot run in parallel while supplying power. Either the mains or the generator will be supplying power to our domestic load. Now, why is this done? This is because we cannot, or we are not in a position to match the generator supply to the main supply so that they can run in parallel. This happens because we are not able to synchronize both the power. Now, synchronize in layman terms means match. So we are not in a position to match the generator power to the power coming from the mains. So we cannot run them in parallel. When our incoming generator has attained the desired voltage and the speed or frequency, we are ready to deliver power to the grid. Grid is the interconnection of generating and substations. Power is already available in the grid. So here we are going to match two independent sources, one our generating station's power and one that of grid. So before we send power to the grid, we need to match the various electrical parameters of grid to our generation, and then only our generator can run in parallel and start delivering power to the grid. Basically, there are three parameters that we check before synchronization. One is the terminal voltage, means at the voltage level which we are synchronizing to grid. Second is the frequency, means what is the frequency of the grid and what is the frequency of the incoming generator that needs to be synchronized to the grid. And third is what we call phase angle, but this is not exactly phase angle. It is whether our RYB phase of the incoming generator and the RYB phase of the grid is superimposing on each other or not, or whether there is any angular deviation between the R of incoming and R of grid, or Y of incoming and Y of grid. So these are the three parameters that we need to check. Now why we check this parameter? First, coming to frequency. Now as per generator definition, generator converts mechanical energy to electrical energy. Now input is mechanical energy. What form of mechanical energy? It's rotational mechanical energy. Now rotational mechanical energy, we denote it by rotational as number of turns per minute as frequency. This means generator input we are giving frequency based thing and we are getting output as electrical energy. So there also important term is frequency. So when we are trying to synchronize our generator to that of a grid, we need our generator to be at a slightly higher frequency than the grid. Let me put it this way. Suppose the grid has a frequency of 50 Hz. So what we'll do, we'll put our generator at a slightly higher frequency. Suppose 50.1 Hz or 50.05 Hz. So when our generator is at a higher frequency than the grid, then this is the parameter that decides the flow of active power. Active power flows from higher frequency to a lower frequency. So when we are trying to synchronize our generator to grid, this means we are trying active power to go from generator to grid, so that our equipment functions as a generator. If there is a reverse direction of flow, means if the active power flows from grid to generator, this will be the motoring action. And if we keep the frequency same, suppose the grid frequency is 50 Hz and our generator frequency is 50 Hz, this is a floating condition and no flow of power will take place. So while synchronizing our generator to grid, the frequency of the generator needs to be slightly higher than that of the grid, which this will decide the flow of active power from generator to grid, or in other words, this will decide whether our generator will function as a generator or not. So frequency is a very important factor in this. Second parameter which we are talking about is voltage. So when we have switched on our excitation system, we get generator terminal voltage. Suppose our generator terminal voltage is 25 kV. Now generator is connected to generating transformer, and this generating transformer is then, after some electrical equipment CTPT, it is connected to grid via circuit breaker. So while synchronizing that, we gave a closing command to this circuit breaker. Suppose we are synchronizing our generator to a 400 kV grid. We have a 500 megawatt generator, generating terminal voltage is 25 kV, and generating transformer will step up this voltage to 400 kV. Now, voltage is a parameter that decides the flow of reactive power. So, active power will flow from generator to grid, and if reactive power flows from grid to generator or from generator to grid, the generator still remains a generator. But while synchronizing, we try that all the control of our generator in our hand. We don't leave anything to grid, so that if at the time of synchronizing there is any disturbance in the grid, still our generator remains intact. So while synchronizing, we keep our voltage slightly higher than that of the grid. Now let us take an example to understand this. Suppose we have to travel from our home to the university and the road is damaged. So what we do? We wait for the road to be built. It doesn't matter whether the road is built from our home to the university or from university to our home. It doesn't matter. Main work is we have to travel if the road is built. So active work is our traveling, and the reactive power which we are building the road. So this voltage is necessary to keep a voltage gradient so that active power can flow. It doesn't matter whether the generator voltage is greater than that of grid or grid voltage is greater than that of generator. But while synchronizing, we keep our generator voltage higher than that of grid so that we are the source of reactive power at that time. Okay, so if the grid is at 400 kV potential, then we keep our generator and GT terminal voltage at suppose 402 kV or 401 kV. Now coming to phase angle, means RYB phase, superimposing on different RYB phase or not. This is done by synchroscope. Now we have our generator which is running at a frequency of 50.1 Hertz and the grid is at a frequency of 50 Hertz. This means in a phasor diagram, if we see our RYB phase, that is 120-degree phase displays, is running at a faster speed than the grid RYB phase. And so if it is running at a faster pace, then a time will come when this will overlap or superimpose on the grid RYB phase, and after that time it will again pass that. So we need to close the breaker at the time when the RYB phase of the grid and RYB phase of the generator superimposes. Now if the generator frequency is greater than that of grid, the synchroscope equipment which we are calling is used for synchronizing will run in clockwise direction, and if the grid frequency is greater than that of generator, it will run in anti-clockwise direction, and the speed of rotation will be the difference of the two frequencies. So when we need to synchronize it, we need our frequency to be greater than that of the grid. So the synchroscope movement should be in clockwise direction. So after that, when the synchroscope is in clockwise direction, and there will be a mark in the synchroscope that shows that dark, it will be highlighted that at that point we can close the breaker, and at that point when the needle comes, the synchroscope will be giving us a permit to close. Now closing the breaker can be either manually or automatically. So when the three things matches and synchroscope gives a closing command, we close the generator breaker, and once the generator breaker closing command goes, generator breaker will close and our generator is synchronized to grid. The capability curve of a synchronous generator defines a boundary condition within which the machine can operate safely. It is also known as operating charts or the capability charts. The capability curve basically defines the thermal limitations of the generator. It indicates the operating parameters like megawatt, megavar, kilovolt, that is terminal voltage, full load current, kiloampere, excitation parameter like the field voltage and field currents, power factor, load angle, and operating margin of the machine. Capability curve of a generator defines the boundary within which it can deliver reactive power continuously without overheating. Generator rating is specified in terms of kVA and power factor at a particular terminal voltage. Active power delivery is limited by power delivery capacity of the turbine and heating of the stator winding due to flow of current. Reactive power, which a generator can deliver continuously without overheating, is governed by three parameters: armature current limit, second is the rotor current limit, and third is the end part or the end ring heating. Each and every synchronous generator is running on capability curve. Capability curve of a generator is provided by the OEM, that is original equipment manufacturer, and the curve is decided during the type test of machine during its manufacturing process. Now we'll try to draw a capability chart of a synchronous generator. Suppose E is the generator terminal voltage. Generator is connected to a grid which has a voltage V. The reactance of the line between the generator and the grid is XD, and the current flowing from the generator to the grid is I. So as per vector we have E is equal to V plus Ix. Now we will draw a vector diagram for the equation E is equal to V plus Ixd. We draw the grid voltage V as a vertical line. This is represented in the first diagram as OA. The current will be lagging this voltage by an angle phi. So we draw the current I at an angle phi from V. Now Ixd, the voltage drop across the reactance, will start from point A and will be at an angle 90 degree from the current vector. So we get AB. Now E will be obtained by adding OA and AB. That will be the vector addition. So we get E as OB. So here we get a voltage triangle that is represented as OAB. Now we'll convert this voltage triangle to current triangle. To convert voltage to current, we need to divide it by impedance. So we divide this all sides of this triangle OAB by XD. So what we get? We get OA as V by XD. We get AB as I, and we get OB as E by X, or E by XD I mean. So this is the current triangle. Now we convert this current triangle to power triangle. To convert this to power triangle, we have to multiply it by the grid voltage V. So we get OA as V square by XD. We get AB as VI, and we get OB as E into V by XD. So our final triangle which we are getting OAB is the power triangle. Now in the fourth diagram, in the right hand corner bottom side, I have represented various angles. Since the Ixd in the initial power triangle was at 90 degree to the current, so I have represented 90 degree. In such cases we can see that we get a vertical line Vi cos phi as the active power, and the right hand side red line as Vi sin phi, that is the reactive power. So we get P and Q. Now before we go to the capability curve, we need to know about the four quadrants of the PQ axis plot, that is active and reactive power axis plot. For this, we take active power P as the x-axis and reactive power Q as the y-axis. So we get four quadrants. In the first quadrant, active power P is positive and active power Q is positive, reactive power Q is positive. In second quadrant, active power P is negative, while the reactive power Q is positive. In the third quadrant, active power P is negative and reactive power Q is also negative. In the fourth quadrant, active power P is positive while the reactive power Q is negative. So in the first and the fourth quadrant, where P takes the positive value, makes for the generating mode as it generates active power, and the second and the third quadrant, where P, the active power, is negative, makes the motoring action. A synchronous generator should never enter the motoring mode. So for capability curve, we will consider only the first and the fourth quadrant where the active power P is positive. As earlier discussed, the capability curve consists of three limiters. One is the stator current limiter, second is the rotor current limiter, and the third one will be the end ring heat or end point or end part heating limiter. So we plot the first limiter, that is the stator current limiter. For this, we take x-axis as the active power and y-axis as the reactive power. So we have the P as active power and Q as the reactive power. Now earlier we have got the formula that power is equal to VI cos phi. So taking VI, what it will be? It will be the MVA rating of the generator. So with MVA rating as the radius and center as origin, we draw a circle. So this circle will give us the stator current limiter. Now, if we draw a line from the origin to the stator current limiter, this line will be called the power factor line. Means at that instant operation point of generator, at what power factor the generator is, this line will give us. Suppose we draw a line from origin to the stator current limiter, this will be called power factor line. Why? Because now at the point the line intersects the circle, that is a stator current limiter, we drop a perpendicular to the P axis and Q axis, then we can get the active and reactive power, and taking the tan phi will be reactive power by active power, and then we can get tan inverse, will get phi, and cos of this will be the power factor. So at that instant, at what power factor the generator is running, we can get it from this power factor line. If only this limiter existed, then we cannot in any case get more current from the or the more active power from the stator, because if we increase the generation or what we call load of the generator, it will cause overheating of the windings, which stator windings, and if the temperature of the stator winding increases, we need to trip the generator. So this causes a limitation in the maximum current that a generator can generate. Now coming to rotor current limiter. Now refer to the earlier phasor diagram which we had, from where we got that P is equal to VI cos phi and Q is equal to VI sin phi. Now here we will be for rotor current limiter, so we will be focusing on the reactive power. Q is equal to VI sin phi. This can be represented as, from the phasor diagram itself, EV by XD cos delta, delta is the load angle of the generator, minus V square by XD. You can see it from the diagram itself. So now we need to plot this on the PQ axis. Remember that while plotting this reactive power Q on the PQ axis, we will be plotting only on the positive active power side, means positive P side of this, that is the generation mode, which we had earlier discussed. Now if you remember some polar form of a circle, here this represents a circle whose center will shift minus V square by XT. This means it will shift on the Q axis on the negative side by minus V square by XT, that is V square by X, negative side of Q. So center shift from origin to minus Q side, negative reactive power side, by V square by XD. So we get the center, and our radius will be EV by XD, and then we plot another circle. Now this circle will give us the field current limiter. While drawing this circle, we must notice that the field current limiter will be meeting or cutting the stator current limiter at some point. In this figure, we get a point A where the stator current limiter and field current limiter are intersecting. Now, if from the origin we draw a line towards this point A, then this will again be a power factor line, because any line from origin to the stator current limiter will be a power factor line. And since the rotor current limiter is intersecting this, so this point A will be the rated power factor line. The third limitation that comes in the capability curve is the end part heating or end region heating limit. The end part heating is localized heating at the end region of stator core of generator. This heating is a result of eddy current loss in the lamination of stator core due to end turned flux of armature winding. This heating imposes a limitation on the operation of synchronous generator known as end region heating or end ring heating or end part heating. Basically, the laminations of stator core are so stacked that the air gap fluxes are parallel to the laminations. This is done to reduce the flux linking by the laminations and hence reduces the eddy current losses. But the end turn leakage flux of armature enters and leaves the stator core perpendicularly as shown in the figure. This causes a higher leakage flux linkage by the stator core lamination, which subsequently induces eddy current. This eddy current produces I square R loss, that is the heat loss, and leads to heating at the end points. End part heating is thus caused by mainly end turn flux. We get this curve during the OEM routine test when it is being done in the manufacturer end, and they give us this curve as the end region heating curve. Now if we draw a capability curve, this is how it looks like. This shows a 600 megawatt generator capability curve. So if you see this condition, we have the active power megawatt as the x-axis and the reactive power MVAR as the y-axis in positive and negative direction. If you see in the first quadrant, which we are getting active power positive and reactive power positive, this condition is called the overexcited condition. Why? Because in this condition, in order to send reactive power to the grid, we keep the generator terminal voltage, or in fact the GT terminal voltage, higher than the grid voltage, so that reactive power is being fed to the grid. In other words, the generator is generating reactive power. So Q is plus. So the excitation system is overexcited. So this region is called overexcited region. And as it is overexcited region and it is sending reactive power to the grid, so this is the lagging power factor zone of the generator. Now coming to the bottom quadrant, where active power is plus and reactive power is minus, means we are consuming reactive power. This means we are an underexcited condition of the generator, where the generator voltage is less than the grid voltage. That is, our excitation system is low excited, this underexcited. In this condition, we are consuming reactive power from the grid. This means the generator is running at a leading power factor. Here, the end ring heating effect comes earlier in the underexcited condition. In other words, the end ring heating is less under overexcited condition. And why is this then? When generator is overexcited, the retaining rings of the rotor is saturated. So this offers high reluctance path to the leakage flux. Therefore, the leakage flux to the stator reduces and hence end part heating reduces. But when the generator is underexcited, the retaining ring of rotor is not saturated. Hence, it offers low reluctance path to the leakage flux. Hence, during underexcited condition, additionally during underexcited condition, the flux produced by armature current adds to the flux produced by the field current. Therefore, end turn flux enhances the flux axial in the end region. This causes more heating in the end part of the generator, and this can severely limit the generator operation. So, these three, stator current limiter, rotor current limiter and end ring heating or end part heating, these three combines together to form the capability curve. So this is the end of our discussion on this topic. If you have any queries, you can mail me at kamalnasir.npti@gmail.com or at gov.in. Thank you.